All right, this is going to be this problem take 2. You don't know this, but I had another video that I did that makes me sad that the was it compiler screwed up? It wasn't great. Anyway, so tetherball problem. If I haven't set this yet up for you, here's what I want you to do. I'm going to give you the problem. I want you to hit pause. I want you to try to do as much of it as you can. You're probably going to get stuck somewhere, but that's fine. So you hit pause. You'll try it. Get stuck for a little bit, unpause, and we'll do the rest of the video. So here it is, okay? Hopefully you didn't already hit pause, because I haven't given you the problem yet. It's a tetherball. If you've never heard of tetherball, there's a giant post. Hanging down from the post is a ball. There's some base right here. And I'm just going to give you a couple of basic numbers, and I want you to try to figure out something that seems a little bit more complicated than that. The first number I'm going to give you is that hanging from the string, this guy right here is 18 degrees. Let's go to the side. Let's see, that's angle. Angle is 18 degrees. The only other number, the length of the string, we'll call L. It'll be 1.4 meters. Now with that, if you've ever played tetherball, something you may have noticed, maybe not, is that if this is the case, if it stays at about 18 degrees, another way to put that is if it stays at about the set amount of distance away from the pole, it can only do that at a very, very specific speed. So what I want you to try to do is figure out what is that speed that the ball has to be traveling to go in a circle. So go ahead and pause that video now and see what you can do. If you didn't pause the video, this next part's going to be weird. Welcome back! Hopefully you did well and you got the right answer. Let me just go ahead and throw out the right answer. So maybe if you got it, you can avoid listening to me a whole bunch. I believe it's 1.18 meters per second. Let's find out. I'm not positive on that one. But I think that's about right, 1.18. For starters, don't know what to do on a circular problem? First thing you do is look for the circle. This last problem that I did in a video is the plane going through a horizontal loop. Acts very similar to this one, so you might want to watch that one first even, and then maybe watch it after. But it's going to be remarkably similar to what it is we're talking about here. And in that I talk about the perspective that you're coming from. And you've got your options of top, side, and back behind that particular object moving forward. In this particular case, in order to find the circle, we would have top. That'd be kind of the center pillar right there. The ball is kind of going around like that. The velocity would be moving, say, that way at that time. Obviously, different spots at different times, and the acceleration is towards the center. This would be our top point of view. Now, the reason why we do that top point of view, or to look at the circle, is then to go, okay, when I look at the forces, what's the direction of acceleration? Now, luckily for us, we've already got a side view right here, and that sets up us very nicely to look at the forces. Of course, there's going to be force of gravity straight down due to the Earth, and we're going to have tension coming up right along that pillar right there, right along that rope right there. And like I said a second ago, where does the acceleration belong on this diagram? Well, it would be towards the center of the circle, so it's going to be that way. Now again, I'll reiterate, we don't usually draw the acceleration on our force diagram. Whenever I do it, I always do it in a separate color, and then I pretty much immediately erase it. But it's good for you to know because you've got to know what direction the net force is in, and this also helps us to see, hey, there is no acceleration in the y-axis. Pivot. So let's get rid of that. Now, as I look at the numbers given to me, as I look at my force diagram, as I look at my circle, or as you did the same, you might go, how on earth are we probably going to get speed? Okay? If you don't know, let's just throw some things up there and see what happens. Where do we start? Let's start with sum of forces. I'm going to sum the forces in the y equals mass times acceleration in the y. As I addressed just a second ago, there is no acceleration in the y. It's only x. So that would cancel. And what are the sum of forces in the y? Well, we have negative force gravity. Now, I've been talking a lot about positive towards the center. You'll notice that we're not really addressing towards the center here. Okay, towards the center would be this way. So I don't really need to worry about different positives or negatives here. I'm going to get negative force of gravity, and then positive force tension. But we have force tension in the, let's say, in the y and in the x. So this would be positive force tension in the y equals 0. That doesn't help me. That doesn't tell me anything yet. So let's try to sum the forces in the x. Okay. For starters, is there acceleration in the x? Well, yes, we saw that just a minute ago. Okay. Next thing, especially after this chapter, you also need to ask with that is that a centripetal acceleration? Well, we can see from this diagram here, from the top-down view, that yes, it's perpendicular, it's towards the center, it's changing the velocity, so this is centripetal acceleration. What does that mean? Well, we already have something to now aim for. Velocity, how fast it's going, is in the centripetal acceleration equation, if I write that right over here. So if I found centripetal acceleration, that might help me to finish the problem. Okay, so let's keep going here. Trying to find acceleration. What is the sum of forces in the x? Well, there's just one. It's force tension in the x. Now, one thing I might point out right now that you might have noticed that we're missing is mass. And probably typical to a lot of stuff in chapter 4, if you don't have mass, more than likely it's going to cancel. So let's just go ahead and leave that alone for right now and see if we can't find something about force tension in the x. How do we solve for force tension in the x? Well, if I can't use this, and obviously I can't, I come up here and I see the triangle. See, okay, this was, let's see if we can't, actually, you know what, let's blow this up bigger. Here's force tension. So this would be force tension in the x. This would be force tension in the y, and of course, oops, y rather. And of course, this is our angle 18 degrees. I might be able to pull off trig, but I need to know one of the other sides in order to get this one. Hey, this actually might not have been pointless after all. We see here that force tension in the y must equal force of gravity, which is equal to mg. And again, yeah, we don't know m, but let's hold on as though we do. We basically say, hey, this guy is the same size as mass of gravity. Okay, so let's get force tension in the x. I have an angle. This would be the opposite. That would be the adjacent. So tangent of 18 degrees, as opposite and adjacent, is equal to opposite force tension in the x over the adjacent, mg. Do a little bit of algebra. We see force tension in the x is equal to mg tangent of 18 degrees. Okay, so we have something for force tension in the x. Let's go ahead and substitute that in over here, and we get mg tangent of 18 equals, hey, looky there. I got a mass on both sides, and it's going to cancel. So acceleration should really just equal gravity times tangent of 18 degrees. 8 times tangent, 18 degrees. So the acceleration on that guy should be an acceleration of 3.18 meters per second squared. It's not super clear to read. So now we have acceleration. We can come right over here. Now we don't yet have radius. You might notice that we haven't yet used length, and you might say, hey, that's the length, except remember the radius is literally the radius of this circle. So again, if we transcribe that up here, that is going to relate to this guy. Now we don't have this guy, but we do have an angle. It does have the exact same angle as this inner triangle of forces. And we do have one of the sides of 1.4, so let's just go ahead and use trig to get this here. Let's call that r. This is opposite of the angle, and that's the hypotenuse. So the sine of the angle is equal to opposite r over hypotenuse L. So radius is equal to length times the sine of angle, or 1.4 meters sine of 18 degrees. 1.4 meters. Sine of 18 degrees. So this radius is 0.43 meters, about 43 centimeters. So that kind of makes sense. That's how far it would be from the pole. So let's come over here. Now to find the speed, all we got to do is a little algebra. multiply r on both sides, square root both sides, and you're going to get your speed. So that is 3.18 meters per second squared times 0.43 meters. We square root the whole thing, and we find out how close spin hour was at the beginning of this, actually telling you the right speed. I was getting all funky. 1.17 is what I have here, but it kind of depends on how you round. So yeah, 1.17, 1.18 meters per second is the speed that you're going at. You might have done this a slightly different way at the end. I solved for acceleration centripetal here, found the number, and then went over here. The other thing that you could very easily do is just have substituted this equation in there. If that was the case instead of going for acceleration 3.18, you wouldn't know that number, but you could go straight to the right answer, multiplying r on the other side, square rooting that, and that would have given you VT as well. And that should make sense when you look at my work over here, because we have r times, that's what we found acceleration with, square root to get V. And that is going to end up with the exact same answer as we did just a second ago. And that's how to do that problem.